in Leiden. Yes, this was the site. So the idea was to represent, to have three different kind of section. One on the general representation using the logic, classical, and especially, classical logic. I would say description logic, especially here, play an important role. So this is description logic, well, possibly with UML. And then variation on other way of representing using monotonic reasoning, answer sets, and so forth. The idea is that students already know Prolog when they do this, so they do not need to have introduction to Prolog at all. Because the prerequisite, if you see here, prerequisite is artificial intelligence, and during the course of artificial intelligence, they already programmed with Prolog. Then from there are several other specialized way of representing knowledge. So belief, for example, so going to modal logic. Then events, time, actions, and that means we go to the situation calculus, event calculus, and transaction logic. And then was some application. In preparing the slides, I found this actually a bit complicated because the structure, yeah, especially for example, application in this order is quite strange. One describe, for example, you have a description logic, you have a description of, you define, you give to the students a several way of describing description logic, and that will fit immediately well with the semantics web, for example. Then one could define situation calculus, and then could go immediately well with the cognitive robotics. So at the moment, it's a kind of one introduce all the information, and then you apply the information. So that's do not always have to be yeah, the best way. But okay, so at the moment, so it's put the information as it is in this description here. And another thing is it's really a lot also. This is the course which actually has the largest number of slides probably. There is a lot of information, and it's impossible that one can do all this in a course in 20 hours only. The idea was also to have, on top of this, to have also a practical section to solve some problem. Yeah, the problem may come from this part here, from the last part. Not clear, at least it was not clear to me how this should come. So at the moment, there is nothing about exercise or application, practical section. One can think about it. But at the moment, so we have only a set of slides, which is quite large. So some decision have to be taken, and yeah, what exactly is not fully clear. Maybe we should give it this as a, yeah, everyone should be able to take different approach to it. Shall I compare a moment with the other approach of the AIT, which I don't know, is coming from you, Dung? I think.
No, I don't think so. If you just can say more about that, this would be fine.
Okay.
That would be the standard for all of us, right?
Yeah, well, we have to decide whether it's for me, it's fine. I saw also the way you presented.
It's okay. For me, it's fine too. I don't insist on other things. It would be fine.
Okay, so let's go then to share let me take it to share the structures, and then we can see some slides, for example. Yes, this is. Okay, so this is the structure where is with all the files which are present now are present in the share space. So okay, so these are the three sections we say that there is the section 1, 2, and 3. In the section 1, we have the general definition of concept, what is ontologies and how to represent them. And here I took the slides from Diego Calvanese. Diego Calvanese is one of the most important person behind the description logics. And so he has a very nice set of slides. It's very extensive, I would say. So it's, yeah, you can fill the whole course with these 2 chapters only. And then is the question, yeah, do we want, for example, having application to UML or not? I don't know if the students, when they start, they already know UML. There may be some reason to want it or not. Yeah, that depends. If you're coming from computer science, if you've done some software engineering courses, maybe it's good to see the relationship between them. And otherwise, yeah, one can also forget if you are not from a computer science background or you've never seen UML before, one can forget all this part of UML and just going directly to the description logic. The description logics, as presented by Diego Calvanese, is done in a very formal way. So really with a formal definition of formulas, logics, and all complexity. And I think that this is actually quite important because the complexity behind all the description logics is exactly in the details. And yeah, on the one hand, you want to have a logic which try to describe as much as possible of the word, what you want to describe, the rest of the word. And but the price you pay, the more you want to describe, the price you pay is that the complexity becomes enormous. So it's become exponential, double exponential reasoning about.
But could you show a slide that we can?
Yeah, sure. Let's start with some of the slides. Let's start with the ontologies first, maybe.
Yes.
And just open it. Yeah, I am. That's. They should try to find a way to be faster in doing this switching from one thing to the other. Because I have to find the bottom. Where is the sharing slides? Yes. So here we have the ontology, model information through ontologies. This would be a kind of introduction, really. I have here the PDF. We also have the PowerPoint version of this slide, so I can upload this later. So that's yeah. This is basically what is the idea. Introducing what the ontologies are, then using logic for using logic for representing knowledge, and then some ontology language and UML, and then reference. So that's for this part. And then there is a full part on the specific description language. So yeah, okay, that's why people want to go to ontologies. By the way, just to show you, these are, if you read this number here, it's 145 slides, only the first chapter. So that's and it should be scheduled this in 1 hour, which is basically impossible. Okay, so yeah, that's the way, just to try to introduce why we want to have a logic for describing ontologies and information in general, so knowledge. And as you see, yeah, that's because things becomes the information becomes more complex, and therefore you want to have all this kind of complexity in the logic itself to capture all the facets out there. Yeah, so I don't know if I really have to go through the slides, all the slides. I can go faster on this. So this is the most important thing, so that there will be a full chapter on description logic. So these are tools which are used in semantics web, for example, and they are based on logic to describe the information which is has to be represented. And together with the logic, yeah, there is the whole idea of having this is to have automatic support. So it's interesting to do this logic only if they can be effectively can be used for reasoning. So if you have the complexity of reasoning is too high, then it becomes less interesting. Okay, so what is an ontology? I don't, if you want me to stop in some slides, I just go through the slides faster, let's say, and ontology, yeah. You see this how in general the schema how this could be work out. So this is the basic of a semantic web. Of course, the things become much more complicated than this, but there will be a full lecture on that. That's just to start with, and yeah, so you can use at runtime, at before on the design time, and so forth. So these are all the use of ontologies, blah, blah, and yeah, so here comes things which are important, which formulas you have to choose, that have to be efficient, and there must be tool support. Yeah, that's what I said before. Yeah, you have to have this balance between the expressive power that you want and the complexity on reasoning, because you want to have some automatic reasoning. Yeah, that's okay. Tools. So this is still a lot of yeah, say introductory model, introductory text. Maybe too much text.
Very nice. What you show us, very nice.
Yeah, no, these are nice, absolutely.
Really, I mean, very nice, very appealing. I like it very much.
Yeah, we have it also in the PowerPoint, so that can be easily adapted after. This is a PDF, what I'm showing. These are coming from a course that Diego Calvanesa done yeah, okay, a few years ago on knowledge representation. And this is a course that is not for, yeah, it was for master student, but it's not for a course that he teaches at his own university in, I think it's in Rome. But it just used.
We can't hear you.
Our connection to Europe seems to be cut.
So we all hear except Marcelo?
Looks that way, yeah.
I think so.
Time for more coffee.
Is coffee break now?
Looks that way. Professor Doom, can you share the coffee with us?
Coffee what?
Coffee or tea?
Hi, welcome back.
Okay.
You're on mute. Marcelo, you're on mute.
The internet needs coffee.
So it was not a problem of coffee. I wanted to say,
Oh.
but it was just internet that just kicked me out. Okay, so let me take back the screen.
Welcome.
I have to find out where is it now. Oh, it's also this now. It's gone away. Yes. Put full screen so that. So you okay? So yeah, I was here. I don't know. Maybe I lost you here. I think on the connection between the real world and the formal semantics and the abstraction is the link. And okay, so and then you have the logic, and then you start. You just start with the basic of what logic is and what does it mean to be truths, and okay, all standard things, and yeah, syntax. It's really and standard, but the students at this point they should know already what proposition and predicate logic is, but they never probably heard of modal logic. But this is just at the moment it's just a simple introduction. So it's syntactic also, so that's all grammar, blah blah. That's and yeah, okay, language first order logic, and then yeah, you go to description logic. This is just as an example. I don't know if the students have done grammars, so they know how to interpret these symbols. But they just like a grammar or programming language. Let's say one can introduce or change it in a way that is like introducing a grammar of a programming language. So this is just description logic, and it's one of the many description logic. There is it's called ALC. Yeah, okay, that's at the moment it's just syntax. Doesn't mean anything. Then you have the interpretation, so you have semantics. And until for this is kind of recap for propositional logic and models, blah blah, the truths. Okay, this all standard, and that's all about yeah, basic notion from logic that can be nice, interesting to just recall it at least. And someone I've never seen before, they may be too complicated. But this can also be skipped at this level. So yeah, there are rules. What are inference rules? But this are given in terms of examples. So there is no pretest to have it fully, and different styles, and refutation, resolution, propositional revolution, and okay. So this goes under completeness. So it goes really into the formal world. So we go now to ontology. And so here, one can also skip all the formal part actually, and they can just immediately go to the ontology part. So just say what is needed, what you need to describe an ontology. So syntax, semantics, and some pragmatics. And yes, so well, that is say we know what syntax and semantics are. And yes, so this is all what one need to have: concept and properties and the relationship between concepts. So this the example is always taken in terms of UML. So that's here depends. So how much students knows about UML? Maybe it's in a way easier than describe the logic, but there is a lot of information in a diagram like this. There are inheritance relations, association, there is all this labeling around, and all the information on the classes. So there is a lot of information, and one has to try to put all this information in logical terms. Yeah, so it goes here, the relationship here, we have the several types of relationship that one can describe. At the moment, it just, again, remains at this level of a very high level. And here you have, okay, this is the description of UML in terms of graph. That's maybe what people are more used to, or entity relationship diagrams, also very easy to understand. And but one can try to describe the same things in terms of logics. So it's more syntactic based and more parsable by computer. And for automatic reasoning is easier. And there are several logics. There are too many. All is the one which is used in all and many variation of all, or light and all the other. The one used in the semantics web mostly, but this is always based on terms on one of these logic, description logic there. Yeah, so I think that was just a kind of introduction to ontology and why and what are them and how they use it and how they model. And then if I go to another, try to share another file. So one can go directly to a description logic. So maybe I can start with that, or one can go to describe what are conceptual graphs, the linked data, and then description logic. So let's start with description logic. So since we are in the logic part. I have to share it a moment with you. So here we go really more deep into the details. Here there is much more description of what are really the description logics, and so okay, so there are, let's say, here we start immediately with the problem of complexity. So because this is really why people try to study several description logic. There is not one single standard, and that depends then on the lecturers, on the university, if you want to do this or not. So this could be skipped at all the problem of complexity, but at least it should be mentioned that yeah, complexity really play an important role in the description of ontology, in which language you use for describing your ontology. So if you want to do reasoning with some automatic way, then yeah, you have to decide carefully which logic are you going to use it. Otherwise, you go immediately to undecidable problem or to problems which are exponentially, the complexity can be exponential or even double exponential. So that's why it's important to have a clear idea of that. I know that this is very, very formal. So that's if someone may want to skip it, just can say in words that it's easy to describe the problem in words without going to the detail or exactly what does it mean computational complexity and all these things. So here goes really in terms of Turing machine and asymptotic behavior, what again, this need not to be said, all the complexity classes, how this works. So this is a kind of recap of complexity theory. So there are polynomial time and NP and so forth, all these definitions. And again, I understand that this may be too much. So this is then becomes maybe a bit more interesting, even if it's also this is quite formal. So yeah, what are the description logics? And that's the most important thing, that you have two things, you have concept and roles. So let me just move it. So that is what you want to do is basically this. You want to talk about some kind of label graph. And you have arcs which represent something, some kind of relationships. You have labels, and you have nodes which are structured things that you want to describe in some way. And then you want to reasoning about these things. Okay, so these are the several examples of the logic you have it. So this one, it's a kind of elementary logic. Then you have some ALC, which is more interesting, and exponential time. So from here on, things become more complex, and you see all immediately is already on another level of complexity. That's too much. This is how things work. Yeah, that's how things can be described. You have what are called the T box and the A box. So for describing objects and relationship, and then they are used. Then you want to know if an happy father means that there exists a child, just such that is a doctor or a lawyer. Okay, if you want to have a child which is a doctor or a lawyer, this kind of relationship. So here is how things works a bit to try to have it. So this is what is called the knowledge base. You have these terminological boxes and the A box. And then on top of on this knowledge base, then you can do some inference. Okay, so things works. So here you have your syntax and how the semantics is represented. So you have some domains and with some interpretation function for the variables. And then then you describe, for example, that you have some atomic concept, and then this is a doctor, and the relationship is just a relation between atomic concept. Then you have negation is clear, conjunction, and then you have all the existenza and the value. Oops, sorry, I moved. And what's called this value restriction, the interpretation. Okay, one has to go into the details to get all this. So it's a kind of restricted existential universal quantification. So that's the basic things. But then you put on this all kind of constructors, so you have this. This is the logic AL. We have seen it until one. So if you put the disjunction, that you have ALU, ALE, all these other things. So you take the atomic proposition and the roles, and then you put all this other information, and you get several logics. And there are even more than this, but just one get all the different logic on top of this, and the semantics is always represented in these terms. So yes, some examples. I don't know how much do I have to go into all this. And then, what is a model? Okay, so then you see all kind of reasoning. So if you have the basic logic or the logic with the negation, then it's just p time, polynomial time. As soon as you introduce disjunction, immediately you go to some NP complete problem. So that's immediately is too much. And unfortunately, you want to have more than this. So the logic which are interesting are logic like this level here. Okay, so here then some examples of some description of the description logics. So this is in terms of examples, and how to semantics is given formally, the model is given formally, and this unique name assumption or others, and then the reasoning. So it's all the reasoning in terms of semantics. I don't know. Yes. So that this may be interesting from the logic point of view, that one can translate the description logic in terms of first order logic, mostly, not all. Sometimes you need a bit more than first order logic, but so that how can one translate one into the other? So if students are familiar with the first order logic, then this can be interesting. Otherwise, one can also skip it. So the other things, yeah, the other things. So the relationship with modal logic. Yeah, that's. I don't think the student knows anything about modal logic at the moment, but yeah, this basically what does it mean, this interpretation. But so it depends. One has to go to the slide and see what is the knowledge of the students they have it for every particular things. Yeah, so this is maybe more interested the OOL, that is the web ontology language, and how this is related to description logic. And there are several versions of OOL. There is not just one. So this OOL Lite, which correspond to this description logic, and then you have all these components. One is, I don't know, yeah, is here, and other things where you have even more richer language. So, but this gives a bit of an idea how complex language like OOL already are. Yeah. So, but OOL is an important language, and so they use different syntax and different, but the semantics at the end is the same. Okay, so and here is just more on. This is more how to translate UML diagrams into logical formulas, which are parsable by computer. So, okay, then it goes in all possible way of the describing these things. So, okay, that you see that this is. This again depends on how much the student knows UML. So if someone is familiar with UML, this can be interesting. Otherwise, all this part can be skipped without problem. And then, so these are all the part of the description logic. So if I put back a moment where we are to just give back an idea of where are we. So what we described now is just 2 chapters, two lectures. The first unit, ontologies, and the lecture 1.4, the description logic. In between, there was some lighter slides on what is a conceptual graph, so what are nodes and arcs. So this is just a very light version, and what is linked data and the semantics web. So that's just to represent the semantic web, how semantics web work in general, and how the idea of having these nodes and arcs, so the graph representation things, they just are enough to represent knowledge with some tags, and enough to represent knowledge which is used in semantics web. So this was so this basically covered this first 4 parts, which is already a lot, but a lot of things can be skipped, and one can try to have only the things which are interesting, depending on the teachers and the pre-knowledge of the students. Then there are some slides on other way of reasoning. So non-monotonic, which comes often in when you have a description of knowledge. So non-monotonic reasoning, answer set, and this case-based reasoning. Is there anything you want to see from that? So these are, especially case-based reasoning is, it's maybe.
Could you show something about case-based reasoning?
Yeah, so I can show you some case-based reasoning. Let me just. Yes, 1 second, I put it. Okay, so this, let me share it now. Case-based reasoning, yes, that's here. Okay, so let's put this. So, okay, so do you see in a full screen now? Okay, so So that's the idea was to really make a bit of a difference between model-based, rule-based, and case-based reasoning. And that's it's interesting for this part of the course. I think this is something which should be interested for the students. Okay, so what is knowledge, but this part maybe is already known at this point of the course. And then you have model-based and rule-based knowledge representation. So let's start with the model-based. Yeah, model-based is clear. Basically, you have to have a model, mathematical model somewhere, and then you try to model it. And so it's something which is really mathematically based, let's say. So like the one we have seen before. And so you transform your word in you have already some representation of the word. If you give a problem, you try to reasoning, and then you get the solution. Okay, so I don't know how much. Sorry, I have these things goes on top of my slide. How does it work? Yeah, so here is a typical, just an example where everything is already there in the model. You only have to run it with the specific inputs you have it, and then the things comes. The typical example is just a digital circuit. Everything is already predicted. There is no problem. So if you have full knowledge of your system, of the environment, then the things just, it's a question of running the system. It's just like a function. You apply the inputs, you get the solution. That's a model-based system. Then rule-based is when you represent the knowledge in terms of rules, like if-then part. So you have if something happened, then you have this, and that is more a prologue kind of like. But things can be just a little bit more complicated than just if then, but because you can have several antecedents, but you can have also some decision you can have. And yeah, okay, so this is just an example of how things works. And if you have this and that, then you get some results. And then if you have several things can apply to a certain situation, so several rules can apply, then yeah, you have to use strategies or heuristics to decide which rules you to apply, and then this can be expressed again as in terms of a system. So this is just basically the old way of representing expert system that's the okay. So these are things bit works in a rule-based system. So the knowledge is in terms of if-then. You have a database of facts, and then you just try to infer some information from it. Okay, and then how it works, this reasoning, okay, you can have this matching and forward or backward. And okay, this is just a standard. Also, actually, these things have already been done in the artificial intelligence course if you do forward or backward search. But it's good to re-see it again in a different context. And okay, so that's when you have conflicts and so forth. So okay, so this is all about rule-based. So that's the advantage with respect to model is indeed that everything is just easier to understand, to represent in terms of rules. But it may be also that you do not you are not certain that you cover everything, of course. And indeed, especially at this point, that sometimes it's easy to write rules, but you want to write a lot of rules, and then you don't see anymore the relationship between all those rules. Okay, so then you go to case-based reasoning. And yeah, that's just learning basically by some examples. So okay, so that's you don't have rules, but you have a case base, so some a set of examples, and then you have some kind way of matching what the environment gives, and this matching need not to be precise. And once you match something with your case, then you can deduce new information about the specific situation. So this is very successful. And here we are not talking about, there is no really machine learning of anything. So this is just a simple way of try to matching things with target with some examples. How it works? So yeah, you have to try to find similar. So you have to find some similar case, and then from that you find the solution to your problem. So it's a typical classification problem. So you have only to find this way to, given a problem, given a problem, how this match to the solution that you already have it. There is some nice example, after. So this, where it's used there, for example, and okay, this how it works, the whole cycle, and how it works. So yeah, okay, this is all the steps they want us to do it in building such a system. And yeah, here goes now indeed to more how to find the matching, because that's all the major problem. And yeah, this is the one that can use the nearest neighborhood or other things. So yeah, for example, how to use the similarity. Yeah, there are some way here how to measure similarities. It can be based on some numerical features, symbolic features. And maybe it's good if we go to an example that so you have to adapt. Sometimes you have to adapt because the things do not match exactly. So okay, yeah, that maybe this is a nice example. At least I found it like a nice example. That you have a car, you have this is a car. You have some cases that describe some fault in a car. You have the front light not working, and it depends if your car is a Passat, it's 2000, that this is the battery voltage. Yeah, you have full information of a problem and a solution, but then you have something which is not completely matching everything. You have also not complete information. So that is, you don't know, for example, the state of the light switch. You have some information here which do not fit exactly. So it's a new problem. How do you match this with the case you have it? Okay, one has to try to find the similarities here, and one has to try. Okay, the similarity by labeling in this case. But you see that this is a Passat, this is a Golf, and the problem is different. This is the brake light, this is the front light. So they are not very similar, but one can try to label this information with some quantitative information. It's important, it's not important, and give even some numbers. And then you calculate in some way the average, the weighted average. And if you match with one, you get some average here, which is case one, it's 0.87. Here it's 0.59. So you choose the best one. And then you say, well, it must be, this is a possible solution. So this is what's called case-based reasoning. You just have some way, in this case it's weighted average, but need not to be weighted average, to just match things. And then once you have it, yeah, you just store your new problem there. So your database of knowledge grows, and the next time you have more knowledge and so forth. So here's another things when you want to buy houses, and there are prices and different types of houses, and now you want to know what would be the price for an house like this. Yeah, what would be it's not immediate because the things do not match fully, but then you have to try to find some kind of matching or partial matching, like we did before, some weighted average, and then you do, you compare all things, and you get the estimate price should be 32,000 pounds. What is this? Okay, so this is basically what is case-based reasoning. That is more flexible, is allow also for not having full knowledge of the system, and this is still very elementary, but easy to understand for students, I think. Of course, all this can be done with more information, putting more quantitative information on top of it, but for the moment, that's fine. And yes, what are advantage and disadvantage? Yeah, this the major problem is that you have some bias here, and that can be a major problem actually. So it depends all on how good is your test case, your cases are, your example case. So that's all case based. If you have any questions, I go back to the material. So you see, so this is basically the first part. This covers the first part. We have a lot of logics, some non-standard way of reasoning, and then even something which is fully non-logic, which is more on approximation similarities based on case-based. But to introduce this, it's nice to introduce this by means of comparing with the more standard system, like the rule-based, the model-based. And then from here, we go to more specialized knowledge, which is when we arrive, when we talk about knowledge, that depends on what we have here. Here, for example, we have the first time we talk about belief. So it's a kind of model logic. So here we introduce a model logic and several types of model logic to talk about belief. Here we talk about event time, and which means, yeah, we are going in the direction of different types of calculi with the when you talk about event time, and then going to the situation calculus as one of the solution for this. And time is just not just time, real time, but just this step by step how the things are described, the one in the order on time. So situation calculus, and then you go to event calculus as another solution for this. And the frame problem, here comes all the things that are known, the problem which are in this type of calculi, that is the frame problem being the major one. And then, yeah, then we have the application. So I don't know if you want to see something from there. I cannot hear Dun. If you can put the microphone. Yes.
Can you show something about action and event?
Yeah. So let me take it 1 second. Action, event, and time. So yes. Action, event, and times. Where is? Oh. I have now too many windows open. I have to find out where is the one. Yes, found it. Okay, so now you should be able to see this one. Yes. So that basically, yeah, so let's just move it to it. The non-monotonic reason they have already seen it. This is just a recall of what non-monotonic reasoning is. And so at this point, so let me see what, I don't remember now what's happening here. Okay, yes, so wait, I put these things here. Yeah, so here you talk about, sorry, you have The typical system, when it's sequential, you have just to go from move state, 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 and one after the other. Nothing can happen in between. And the action is what move from one state to another. And so you can reasoning about the state by just reasoning about the movement of the action, of what you perceive from the action. When you just move from this to a concurrent synchronous system, things basically do not change much because it's a concurrent system, but synchronously. So they change all the action at the same time. So that remain easy to describe things. But when you go to asynchronous system, then things get more complicated because the state can change while going from one action to another. So yeah, but the typical problem from concurrency, the environment can change the state of the system because it's concurrent and asynchronously. So, and then means, yeah, describe, so this is just an introduction to how do you want to describe the evolution of a system in terms of the action that you have it. So if you just have a sequential system, is easy in that just you can just describe the action. But if you go to a concurrent system, then yeah, things are more complicated. You also have to describe the state and the possibility that the state can change from one to the other due to the environment, not to the system itself. Yeah, so that's a bit saying how it works. And yeah, this is the T represent time. So you have how to you have the evolution in terms of an agent, the evolution of the state of an agent, how it works by just updating the time. So once you have the time -1, you perceive in the time the change, the time T, then you can create a model for the time T and so forth. So these are work about reasoning, and things get more complicated if you have a synchronous system, and so then yeah, you start talking about action. So what they call the fluence things, the relationship that change, and the things which do not change, the eternals. Yeah, so yeah, you have all things about the event calculus, the situation calculus, so how the things are related. And at the moment, well, okay, transaction logic, what we say. Okay, this just a very simple, this was just introduction to just go to the next lecture. Maybe I can put that to introduce the other lecture where you have introduce the event calculus, situation calculus. So let me just put that one maybe. I close all this system. We have too many windows open. Situation calculus. Yes. Yes, so now we are here. Okay, so situation calculus, and yeah, it moves with the what is the idea, and it's due to McCarthy in 1969, but it's so it's quite an old things, but it's yeah, you have a situation and actions, and in this way you describe the evolution of the system, and it is used for reasoning of planning of actions, for example. And okay, so that's some examples. So yeah, this is the typical example when I want to describe a situation where you have a stack of two things or two blocks, one on top of the other, and then you want an action which try to move blocks from the top to another place. And then that could be a description of a robot, for example, that just moves things from one column to another one. And you want to describe this in terms of the action and the situation that can be encountered by the system. So in a certain way, you have to think of this situation like being precondition, which makes so that an action execute, and then you have the resulting situation after the action, after the move, is just what a post condition is. Yeah, so that's how the things works syntactically. You have this action. The performance of action is just by do an action. It means that you move from a situation to another situation. And so when you apply this do, you have your action, which is move in the situation S, and then you go to situation S bar. Okay, so that's a situation, action, blah, blah, blah. And then you have all kind of predicates. As I said, you can describe your the change of values in terms of precondition and postcondition. Not for nothing, this comes from McCarthy. So that's also that is one of the precondition, postcondition idea he had. So, okay, so that's just some examples. Okay, the calculus situation. Okay, so this is described. So you have some action for this. I'm trying to understand what is there. Sorry, it got a bit faster for me. Yeah, so okay, so some examples on you think what we were called just before a positive and negative effect. Sometimes you do something just to not being somewhere. So that's the kind of the situation is just described in terms of a negative way. So it's a kind of postcondition. And then, yeah, one of the major problem of all the situation calculus is this frame problem. And that is, yeah, is described in terms of this frame action here. Yeah, so frame action, this is what say that it remains true when an action is performed. And in the case of this moving blocks from one to the other. So you just they try to describe what does not change. And yeah, so, okay, so this in general create a problem. I try to find out where is it. So sorry, we have all this axiom. So this is very important. So you have the effect, what that is the given an action you what change, the frame action that is what remain unchanged, and then okay the successor state. And this is a problematic thing because this is not always. First, it's complicated to say what does not change. So that was one of the major criticisms for the situation calculus. Okay, so well, that you have to have some domain knowledge to have the idea of what does not change, for example. And yeah, so here just a list of problems that are attributed to the situation calculus, and okay, there are all kinds of problems. We don't need to go into the detail. And then how these things is used for planning. Yeah, so and it's used, for example, here just using a language Golog, that is a variation of Prolog for situation calculus. So okay, that goes all about this Go. You have this special different from the Prolog. You have also this do, which is really executed action basically. And it looks like a programming language. Blah blah. One can use this or not. Planning. Okay, so here we are the Golog, which can be used, and okay, that's basically all. And in the next lecture, then you see. Let me go to the next one. The fact that we have to move from situation to event calculus. And let me take this event calculus. Yes. Okay, so we are there. I am working with a laptop, which is a very small screen, and I have you guys staying always in front of my PowerPoint slides. So I see only half of the PowerPoint slides every time. Okay, so the event calculus, okay, so here starting with a different way of describing evolution of systems, different than the situation calculus. Yeah, because now you describe events instead of change of the states. And okay, so that's all kind of text for all this. Yeah, okay, you have the idea of an event, what are event, and yeah, I don't know how much you have to say about this. This is all represented in Prolog, so it makes it actually even easier for students to understand. So this is the syntax basically of the event calculus. But here is interesting. Yeah, one can use these things. So you have the same example where you have blocks, and you want to put, you have a table, you have blocks, and you want to put all blocks on the table, one on top of the other. And how did you do this? Yeah, you try to describe in terms again of, as before, in predicate with no change and predicate which change in times. So no changes, the table is empty, or the table block is on the table. And then the things we change are just the blocks, the location of the block, for example. And then you have the actions. Okay, so some are risky, some are less risky, and then you just describe given a description of the state, which is just a basic conjunction of things. Then you have a precondition. If the precondition match this, then you have some execution of some actions. Okay, so there are some things about the problem we saw before, the negative effect, the ramification, and all kind of discussion here. And then here is the difference between event calculus and the situation calculus. Then is more expressive, that is more efficient, and okay, then this is where it's used. And then, okay, then we go to, oh yes, so here we move to transaction logic, the other, another way of describing, can be used, not only for this, but can be used for describing evolutionary systems. Yeah, so that's, yeah, there is the typical, one of the problem which happen when you have, and I have to recall this exactly. I don't recall, sorry, I cannot see this in 1 second. What's the problem here? But it tried to describe solve one of the problems of the semantics of Prolog. And that it doesn't want to, seems that doesn't want to take the order there. Okay, so semantics, blah, 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 the connective, and then, okay, what you have this, the conjunction, disjunction, and transaction semantics. That's the most important things. That you just, that everything happens, this like in the database, the transactional things, everything, or just you go backtrack, or you just everything happen. Yeah, I don't know how much you want to see. That we can continue like this. And here the difference between the three things. You have a transaction logic, event calculus, situation calculus, and that transaction logic is more efficient, and that situation calculus, yeah, the difference between the three we can see here. And yeah, so that's basically the idea. So let me take back the material. So here basically we introduce what does it mean reasoning about action and system, and then we have the situation calculus, the event calculus, and the transaction logic, and the comparison between the three things. So that's all. There is no introduction here of probability. So for example, there is no description of Bayesian network, because this I presume is done somewhere else. That's the only things here is just a simple description of system statically, like in the description logic, or the description of knowledge in which change in times, and that's what is done in terms of the event calculus, situation calculus, transaction logic. And then yeah, how this can be applied, and in applying this, yeah, there are several ways that we have for three different application domains. So semantics, web, robotics, and knowledge engineering. And this is just a sample of where these things are applied, and they give more information about what semantics web is, and go more into detail of this. I don't know, anything you want to say? I think that for the students, this can be a quite heavy course. Because of the much logic which is there, but it also depends how one want to present this. I think that this part here is not absolutely a heavy part, and the part which is more formal is the part on this one, this part here, when you talk about description logic, because that really goes deep into the logical argument. So it all depends how much one want to do it. Well, I don't have much more to say. Well, if I kill you already, then imagine the students, pure students. But in general, let me say, really, this is too much material. That's really here the teachers has to select and decide what want to do. There's too much to be done for the students. Dunga, I cannot hear.
Well, I think that except the complexity stuff, I think that it's okay. It provides broad coverage of the basic tools of knowledge representation, and I think it is nice. I think it is nice. Students would basically, when they go to a conference, they would could quickly identify what is what, and etc. And when they got a concrete problem, they may identify what kind of tool they may need. And of course, then in this case, they have to learn more. So I think it's fine. It's fine.
Yeah, that's indeed.
Only the problem of complexity is a little bit difficult to introduce, because you would have to introduce quite a few things, right?
Sure.
To my sense, to a student, but we can drop it, I think. Yeah.
Sure, and again, this exactly what I'm saying, that some part can be dropped easily, or can be simplified in an extreme way, like saying, yeah, something is too complex, or in a real concrete way, something which is not executable in easy time by a machine. And whatever machine it takes, that doesn't matter really.
You just simply introduce just Turing just thesis. Basically say, well, this class can be solved by considered to be practically solvable. And this class can be viewed as more or less unsolvable, and you need to find focus on special case if you want to get a children algorithm to solve it. That
Yes,
would be enough, I guess, when you talk about complexity.
Yes, I
Within
also
this
think so.
course,
That exactly. So if someone, I mean, I'm sure that it will be some students which are interested in all the complexity issues, but then it's just 1 or 2 students at most. So that in general, I don't think we have to put all the students to know all the Turing machine and complexity classes, but just to give some flavor of it, just saying in words is not hard. Going to the formalities is hard. So it can just be say like you point out, to just say that there is also this the Turing thesis.
And I think that it's important also that what we want to talk about in the application, because in the application, when you talk about semantic web robotics and knowledge engineering, in the application, we say that needs certain kind of tool, then we should introduce it. Otherwise, we can kind of introduce it more or less, depend on the time. So in that sense, it is okay. I think that the course is quite nice. It provides broad coverage and broad scope, in which every partner can specialize on what kind of application they want to focus on.
Yes, no, I agree. That was the idea when we designed this in Leiden. We were not very much aware that actually there does not exist such a course I mean, I was not able to find anywhere such a course. I must say that I like actually the course in itself, and I would be actually happy even to give it this course in Leiden. Not exactly like presented here with some variation of it, but in Leiden we do not have such a course, and I think this is a miss that the students should have some knowledge on knowledge representation in this way. And we don't have to forget, I mean, all the expert system until the 70s, 80s, they were built this way. And at the moment, it's true that there is more machine learning and deep learning is taking the big part of artificial intelligence, but on the other hand, there is also what is called explainable AI. Then there is people want also to understand how things works, and especially, for example, in computational linguistics, then people that try to reuse a combination of two techniques, putting together and machine learning technique and formal technique to just try to understand or to reconstruct grammars from for example, from sentences.
Would you talk more about the application?
Yeah, so which one do you want to see? Semantic web?
Maybe just start with semantic web first.
Yeah.
Well, I think all 3 applications you show are quite interesting. I mean, I would like to know more.
Yeah, sure. So let me open it. So. Yes, I have it here. Yeah, semantic web. This. So, do you know? Have you ever heard of Frank van Harmelen?
What do you say?
Frank van Harmelen.
Yeah, I heard his name. I never met him.
Yeah, so he worked at the Free University. So we are in contact. We are in some committee together. So that's yeah, he's the guy from Semantic Web in the Netherlands, and this is a co-worker at Grigore Santoni. So okay, so that's more in a light version. So that is than what we see before. So okay, so we have here is the web. How is this today? Just you use it for searching, and what you use that is the search is just based on keywords, and that's all basically. And there is no semantics, so that's the one would like to have it to have more richer queries, and that's exactly what the semantic web is proposing. And how this works, okay, you have to have this information must be represented in the web. So, okay, let's say I just walk through this. How these things works in general. So why this is all reason why one would like to have it, and this semantic web for electronic commerce, for wiki kind of things, and then how it really works. So that's you have to have this ontology. So you go back here, you go exactly to the point that we saw at the beginning of the course. So you have to have these ontologies and logic and inference on this. And you have to do this on top of a HTML. Okay, what are the problems? So here, okay, some way. This is, you have to have some data, metadata. Okay, and then the ontology. And the ontology, we already saw what they are. And that's what you would like to have it. And that's exactly going through the language, having a language for like the one we've seen with disjunction and some relationship within things. So you have this kind of relationship. Okay, so that's this all is just a web ontology language. So we saw this RDF with one other all, then logic in general, and again also here the problem of the complexity, that things can become immediately too complex. And now things goes and works. So what are intelligent agents? Yeah, so this is the standard way represented by the W3, whatever it's called, the W3 something. The representation of the semantics web. So how things are represented, and you have here the ontology and the logic and the proof and things like this. So that's where all the things that we have seen before, they play a role. And this is how Frank van Armelen like to see it. It's a bit a different way, but okay, so this, it's always the same idea, but just where things should be, how things should be represented. And yeah, so that we should not stop just to the XML layer at the moment, but we have some metadata and also ontology that we have it to represent ontology in terms of language, richer language like all, for example. So these are just a simple language, and this is just for a more extensive language. And then, yeah, okay, try to explain all this layer, because it's well known generating a proof is complicated, but checking a proof is easier. So we can always ask for a proof. So that is it basically. That's I can try to see another one. The robotics maybe is more interesting because there is an example on how to use a simple ontological language for the robots.
Marcelo, can I ask a question?
Yeah, sure.
You cover semantic web twice, right? In 1.3 and 3.1. Why you put twice?
Yeah, but it's not.
Different?
No, then in one is okay. So I can show then 1.3. In one is just mentioned. It's not. There is, for example, not represented what is exactly the standard of semantic web. The semantic web is a standard by the W3C consortium, And yeah, one is just mentioned that that 1.3 just mentioned that there is a semantic web, and the ontology is part of the semantic web. And in this lecture, just present exactly what is the standard, how the standard is defined, and what are the language which are used for this, which is OL and RDF. So it's not, yeah, one can also combine the two things at the same time. That's exactly what I say at the beginning. In this, at the moment, it's like you have all the technicalities, and then some flavor of how things can be applied. But in one can also decide, and maybe it's even better for the students to tell them, yeah, why these things can be interesting, and so to present already at that time a lecture which is maybe not too technical, but just to present what is the World Wide Web, the semantic web.
The semantic web. Okay.
So robotics, yeah, yeah. So also in robotics, yeah, that is what is the robots? This is this agents, and then you have this the environment. So it's a typical example of an agent system, and but you have to perceive things, and then based on what you perceive of the environment, then you have the action. But on top of this, you have also something which has to effectuate the action itself. And this is the more engineering problem. So we are not touching this engineering problem. So how to effectuate an action. That they are to build, to move and harm, for example, to just pick something, but we just describe an action in terms of the software part. So this is just for students, nice to see that you can build your own robots, but they know already this, of course. Then they have this football, soccer World Cup that is famous. And okay, so all things that you have it in a robot, sensor, electronics, and it's a nice just to have an idea of all things which are around why robots are so complicated. Okay, so that's maybe there is everything in a robot, yeah, from vision to interaction of speech, everything is there in a robot, so that's also why so complicated. And then, okay, there is this how to take actions, how to really act, and this is where knowledge representation takes place. Yeah, so the idea here is to try to describe this in terms of a very simple language. So this actually is interesting because it's a simple language for describing actions. It's not complete, it's just a toy things, but for the students it may be easy to understand how it works. So yeah, there is one example just showing that yeah, you have a robot and you have to clean the rooms, but there are two rooms, and one is there with the dust and the other not, and the robot has to clean all the rooms. Yeah, so this is describe the situation where you are now. You are in room 1, you want to clean, and the room 1 is clean. So this is the situation as now. And then, okay, so this is, that's basically all that you have to say. There is nothing more. So there is no uncertainty in this language. And then, but you want to, this is the goal, what you want to do, you want to clean both rooms. And it's important here that there is always not or, but it's something which can be easily implemented by the students, this kind of things. And then, yeah, then they have to describe the action, how to do that. You want to clean all the situations, so that you want to go from this situation to this other situation. So this is similar to situation calculus, basically. Okay, so you represent here all the action of the robots. So that's you describe all possible actions. So this can be a nice exercise for students. just describe all possible action that you have to do for a robot, and then yeah, to see if it works. Yeah, okay, so that's yeah, we see that the robots move from here to there, and then here just sucks all the dust in, and this is the room will become clear. So the goal here is satisfied. And the other example is this block that we saw before, how to solve it, this, and yeah. Also, yeah, you have to be careful exactly how to describe these things. So this could also be a nice example for the students. You do have to describe all things, the situation where you are. So this is the goal. You want to arrive that everything is one on top of the other. And in exactly this order, actually, is B on top of A and C on top of B, and there's nothing on top of C, and the table of A must be on the table. Yeah, so that's and then now you have to, these are other goals. Okay, that's one possible things, and then yeah, you have to have the actions. So you have to take one from the other, and yeah, the interesting, the different from before. Yeah, the action are parametric, so that's the students should know these things. So it should be not a big problem, but you have to be careful when you program these things. Okay, so that's all the action that there are here for this particular example. Here, yet another example of the putting the key in a box. Yes. And yeah. Okay, so then from here, so these are just the description of the system. So one describe the description, then you have to plan, and yeah, you use all knowledge that the students actually have already seen about in the artificial intelligence course about forward and backward planning. And now how that done, you have to work with the action that you have it. You have to make the all possible action you can do. So you are in one, you can just clean your room, suck the dust in the room one, but you still remain there. Or you can just go to the room 2. You can go back to the room 1. You can just clean room 2 and so forth. So this is a simple graph. Now you have to plan your action towards the goal being this one. And yeah, you can do this forward planning and with all the action, okay. And one can see that you need to have some heuristic to decide, blah, blah, blah. Okay, so we don't need now to go to all the detail. This all forward planning. So, but these are just nice example to see where you put in practice the two things: artificial intelligence and the course year knowledge representation. And here backward planning. Okay, they see similar things. Okay, but now you go backward. You just remove things. And okay, so how things works for a backward. So. Okay, so these are all things. Okay, and indeed, this is the conclusion that in general it works also for rather more complex languages that we've seen it, but this is just a toy example. But that's enough for the students, I think, to play with it. So. And if you want to see the last one, let me show, or do you have any question here about this? The only problem in these things is that the best is for the student, these things should be done on pen and paper, basically. There is no really programming. I mean, there is programming, but it's programming on pen and paper rather than just programming in just programming language executable somewhere. Let me take the last one. And I think we have done it. Yeah, that is it. Oh, I don't find this now. Wait. Yeah. Okay, so this is about knowledge engineering. Here is not really something more applicable, but just more as a lecture. Okay, so yeah, so how these are how knowledge engineering works. These are the steps. This is more a soft way to explain the students, I think, to finish the course, that to not kill them too much, and to explain how things works in try to do the various steps that are needed for just then afterward modeling that representing the knowledge. So we have done a lot of representation and inference, but there are all the other steps that need also to be done when you want to build, for example, an expert system. So these are the steps that need to be done to when you have to build this knowledge base. And yeah, so you have acquisition and how it works. You have to take from which sources you have to take it. So it's a bit more of a soft things on representing the steps you have to do in engineering knowledge. So there are several types. You see declarative, procedural, meta knowledge, and what does it mean, and all. So I just scroll through this. So the way you can do acquisition. So this was about the knowledge. Yes. So these are what is knowledge. There are several types of knowledge, and now we go to knowledge acquisition. So it can be done manually, or semi-automatic by some expert, or fully automatic. So okay, just to try to explain in time of diagram what's happening. So how do you do this? Interviewing, for example, how to extract knowledge from people, for example, from and this is say a bit completely different than the style of the other lectures. So, but this is important, especially if in the healthcare world, for example, if you want to build an ontology on based on some problems in some knowledge domain in the healthcare, yeah, you have to extract the knowledge somewhere, and that's is an underestimated effect. So we have a lot of technique how to work, and they are very sophisticated in reasoning and the modeling, but the extraction of the model, well, the knowledge is quite complicated and forgotten because no one maybe likes this too much. Okay, so that's how to expert. That's how this works, and so all it's a bit again I say how you do this and how you then test that the knowledge is correct. They have to create this kind of grids. It's a kind of requirement engineering, but for knowledge. Machine learning, of course, but that's a fully automated way to get this knowledge by examples. Case-based reasoning we have seen. So this and so that's all. So this will close the course more in in a soft way, so the students can just relax and prepare for the exam.
Thank you very much, Marcelo. I mean, I like what you presented a lot. I give a broad coverage of many things, and every Asian partner would have a framework so as to attract what are more specific. Yeah, but and the slide are quite detailed, so quite good as well. I think it's quite helpful. But one question I would like to ask you about is what we have discussed our way in in last project meeting is that at the end of the day, we have to submit to the EU, to CEA, training material, teaching material, learning material. So when, what would you say that, how could we extract from what you presented and let's say teaching material maybe, but learning material and training material, how do we get it? I mean, how could we extract it?
Yeah. So I think I remember my idea is that at least how I see these things is that in the lecturing, the lecture material is clear. So just the slides here, for example, this. I think that the discussion that we are doing now, and then maybe we will do later on in the next phase, this is what I would call the training material. That is the fact that we present the material and we discuss, for example, several decision points like we have done now today, saying, yeah, this material could be eliminated, the complexity part need not to be done, or it's there, nice, but can be done in a soft way, or that particular section is the one which is can be skipped in the cases you have no shortage of time. So I think that this is what I would call the training material. So the discussion and for the recording that we are having on this, I would say that this would be the training material. And so you had the training, and the other was?
I mean, learning material, training material. So for me, I am a little confused about that.
Yeah. That's maybe too much terminology.
Teaching material should be the learning material too. How could it be different, right?
Yes, exactly. Yeah, we can be maybe supplemented with the lecture notes or the books and things like this.
If I could maybe interject, I think what we mean is that we have material that's used for the training of us during this thing, right? Which would be Marcello's presentation, and the session by session list of topics and exercises and so on. And then the teaching material would be things like lecture notes, and then learning material would be additional readings or videos, exercises, etc. So if we can break things into those three topics for the report.
Is it deliverable? Is it something that we really have to submit?
It has to be posted to the VLE. That's what we promised. So yeah.
Okay. Because putting the slides and everything is easy. We can put it in a VLE. Putting the presentation, okay, maybe it takes space, but it's also not complicated. And I think also, yeah, we can put also the structure of the course and also all other information. It's also can be present there in the VLE without problem.
Okay.
Dr. Amalka, what do you think?
From I'm Prabhat here from UOP. Marcelo, can we use some kind of visual interactions like Visual Genome API or Jena API, like because XML, the RDF, OWL integration, so that would be beneficial for high degree of student involvement. So how do you feel that in involving visual tools for this, like especially Protege-like applications?
Yeah, so I think a visual tool really helps a lot, absolutely. So if there are visual tools, one should try to use it because it's, yeah, there is also what is a picture say more than 100 words or something like this. So yes, please, but the problem is that in many, yeah, how can I say, in many of the things I presented, in particular at the beginning, that it's more complicated to have these visual tools. So there are, for example, for UML, yes, and one since we can translate UML into description logics, then this would be one way of working. So that instead of working with the dry formulas, one could work with diagrams. And try to represent the knowledge in terms of diagrams is much easier than just writing down for formula. but I don't know if there are many tools that in general are used for doing this. Yeah, I mean existing tools. There are tools for UML, yes, but not that translated in formulas, or that that step is more an academic step at the moment, and not really, yeah, not yet commercialized at all. That's so I'm afraid that I mean I'm in favor of having visual tools, but it's hard at the moment for the topic that we are discussing now.
Can I add something?
Yeah.
Yes, please.
Yeah. Thank you, Marcelo, for the nice presentation. You teach this course yourself to your students, right?
No.
Okay.
No. No, I'm not. No, I say that actually after I prepared the slides,
yeah.
Which, as you see, I picked up from different places.
Okay.
After I prepared the slides, I actually got interested and said that this could be a course that I could teach. I could teach,
okay.
but I'm not teaching.
So maybe we can invite you to teach our students.
Directly there, yes.
As a starter. Yeah, the question is more towards how students would pursue this kind of material, like how to keep them really engaged in this kind of content. That's related to what Prabhat said. If we can use some tools that make it more interesting for them to learn, that would be helpful. Yeah.
Yes, and again, the problem is I don't have an answer here, because I know that there are not so many tools for this. So yeah, I mean, I know there are always a couple of students which are interested in the format. These are those students which likes to work with the kind of mathematics, you see, and they see also the application immediately. So this is not a problem, but in general, yeah, I think that the course, I agree, would be rather complicated for the students, in the sense that how to try to engage the students here is it's quite a task. The most important thing is probably not to just get into all the technicalities, but just try to remember the student where these things can be used or are used, and especially in for the language, for the logical part, on the ontology representation. So at the moment, the slides do not have many examples, and except the last 3 applications we show, and so it would be much nicer if one could see the examples for little representation of little things. But the problem is that either they are too simple, or immediately they grow, the complexity becomes too complicated to be meaningful. So to have a little ontology, it's always too simple, like what is an animal, so that you have wings or not, and all this kind of thing. But it is just too simple. And when you get a real example, then it gets too complicated. So that's why I still insist. I think that especially for the part of the situation calculus, I think that the example of the robots is a nice thing that the student could do while first one introduced the situation calculus and everything, and the event calculus, transactional logic, and then immediately you go to an example with the robots, because it's simple. There are only 3-4 actions that you have to describe. Still, it's visually appealing, because the idea of this robot to clean the room is something which you can imagine easily, and it's simple enough. I mean, there are 3-4 actions that you have to do. There is nothing more than 3-4 actions. It would be nice to have some kind of example like this also for the description logic part. But that's, I don't know. If I find something, yes, it could be. I will post it immediately, of course.
I mean, your presentation cover a very wide range of topics. And so I think that we should later, when we prepare this one, we should build. I mean, not only for this course, but for many other courses, a work group, so that every Asian partner should try to present their view. How would they view, and how would they think? What is the more important part? Because the topics are very wide. For example, answer set in itself is very large topic with a lot of software. For example, right? Nomothetic logic is a field that people work on for since 30 years. We're still working on it. And so it is very large. So we cannot really focus. For example, if you focus, I wouldn't suggest you to teach both nomothetic logic and answer set. I would rather recommend that you teach logic programming and explain that there are problems that are non-monotonic in reasoning and when how logic programming solve it. And that means you teach logic, non-monotonic logic, but you teach only logic technically, algorithmically, you teach only logic programming because that is only direction that people software. Because there are many logic that are more theory and when tool. Therefore, when we teach, we should focus on the part where we can find tools, for example. So we can do that. So for example, we talk more about logic programming, and then there are a lot of tools there. For example, answer set is one of the way, one of the approach. There are a lot of tools, and therefore I think that it is relevant that each Asian partner should contribute and actively participate in that. And we will have at least 2 more training. I hope we will do it offline, face-to-face. Then I think the problem will become much clearer. But for now, we should, in the next month, each Asian partner should put in what they would consider to be more closer to them in this topic. So therefore, what I would suggest is that we got something like learning material, something like what Marcelo suggested. When we got teaching material, and we would say, okay, what AID would think out from that, what our colleague from Konkan or from
for each partner is
Sri Lanka would consider that. I mean, each one of us put a part of it, what we consider to be our teaching material, something like that. And when we got the training material, the software, we can pick up. So for example, in here there are 2 fields. There are a lot of software is the description, ontology, description logic, and logic programming. For example, a lot of software for us to do that. Yes. So something like that maybe.
I think I'm fully in line with you what you're saying, because I think indeed that since visually is hard, but to engage students is probably the best way to use more algorithmic approach. And then also on the other point you mentioned, yes, that I see this just as a guideline and where everyone can just move as far as you want. But take this as a guideline, just take as much as you want of it, but every partner has to prepare his own material, and then this will be the teaching material. So we can even structure inside that we make it in the share space. Every partner for the next meeting, we have this the different the way of seeing the material for each courses, and so and then we can start the discussion from there for the next time. Yeah, I absolutely agree. So this is actually the best start way. So today, this week, we just presented the material, and this material you can use it as you want it, because at the very end, you have to use it. You have to teach with that, so you have to feel comfortable also with what is needed. And but we have still 2 sessions to discuss this. Absolutely.
I think what we should do next time is each of the partners should focus. We can distribute the work for the next online training, where every partner will have one representative would say, okay, that is our view of that, and we would like to present our view, and then you get more detail, and every one of us would do, let's say, for 20 minutes.
Like in working group like we are doing now, so that is can be parallel.
But what I mean with for the next online training, we not only one speaker present, but almost every Asian partner should present. Present their view and what we would do. In that sense, we get involved in that and we try ourselves as well.
Let's try to communicate this what is tomorrow to the other partners. Yes,
exactly. Yes. It's very important for every course. We should have a work group and we work actively from now on. And I think we will not agree on one curriculum because that would be wrong. But we should agree on the kind of overall content and then each one of us will be clear about what we want and what we would like to see, and then we can help each other, and then next time each one of us will have a chance to present our view, and then we will have to discuss, and then it will become deeper and deeper. And after 3 times, I think well, we all become experts, I guess.
That's very good.
I think. But I think that what Marcelo did was beautiful because it's very broad, very, very broad. For example, it's much broader than what I presented at AIT. I present AIT more like a pyramid, but he provided very, very broad things. So therefore,
but then you have to still compress it back.
Therefore, we don't have to focus. Before that, if you have much more students working on knowledge engineering, then you should focus much more on ontology, description logic, and logic programming, something like that. Yeah. But if you have people more interested in web semantics, and then you have to focus on other things. It depends. It depends on what. But I get that many of us would interested more on the connection of OML, description logic, ontology, right? Because it's connected to software engineering as well. Okay? And logic programming. Logic programming has so much tools. So therefore, we can find so many of them. So many of them.
Agree. So yeah, I think now for now we can stop maybe, unless we have other things to discuss. I'm hungry.
Yeah, I think that tomorrow we should discuss. We should discuss the mode of how we are going to go forward.
Exactly.
After that, I think
it's important that everyone has to agree on how to move.
Yes. Then we have about 1 month to prepare the first draft of what we think. And then I hope in the second online training, things would be much more lively.
Yes.
Maybe we could even shout at each other because we disagree. That would be more fun. It would be more fun.
Absolutely. I agree to disagree.
It would be more fun. Yes. And also each one of us will be interested in one topic. So maybe we should talk about that and then learn from others in more detail. For example, I'm quite good in logic programming. If you want, I can give much deeper knowledge about answer set, logic programming, and things like that. But some of you will be much better. For example, Dr. Thutiporn is much better in description logic, ontology. So she will talk about that. For example, so each one of us will put a topic at our heart and talk about that. It's fine because knowledge representation is about everything. We cannot cover everything. We will cover what we think is relevant for the student in our class. And so I think that we should teach more about logic programming and ontology, description logic, because they give a student the tools. The tool and semantic web, that are the thing that they can go and apply. Yeah. And you can do also advanced stuff, but that is up to the individual partner. So we can focus, and next time we can focus on what we call to be the key topic, right? Where we think that more would agree on that, and then we will focus on that. But for next time, and if you do for face-to-face, then it's much more fun. You can do it not only 2 hours, you can also do tea and beer.
Amalka, we want to come to visit you. keep the island safe. That we can come.
I was at a meeting many years ago. I saw two of the leading members of my logistics programming. We almost shout at each other because we don't agree on something. One say this approach it should be the main approach of logistics programming. The other say no, this approach. And we cannot. After that, we don't talk to each other for a couple of days. And it was very fun. It was very fun.
I also like it actually.
But the point is, I was a junior researcher at this time. When I learned when fighting like this, I learned a lot of motivation. Why we say so? Because when we have to argue, something like that never said in a publication. Never said. And so you learn quite a few things. You learn quite a few things from those discussions.
Yes, and also you have to put your argument very clearly. That's.
Any other questions? Dr. Chaklam?
Bararat, do you add something?
Yes.
Actually, I have some questions, but okay. So actually, I see that
on your video.
Oh, video. I'm in the garden for now because my daughter in a room. Okay. I just comment your lecture. Actually, it's cover all and more detail and perfect. Okay, but I just concern a new lecturer in this course because like so hard to imagine the how to design ontology. So I have just to introduce some member like can I share my screen?
Yeah.
So, but actually I'm don't teach in course. Then okay. I'm not sure how gonna share.
There's a button, the green one. Yeah.
The green one. Oh my God. So I'm not sure like the. Do you know Protege?
Yeah, I've heard. No, I don't know which I heard of it. Yes.
Yes. Protege is like the kind of tool for ontology design. It's
Okay.
I ever do research some put some design when you new researcher in ontology is this tool is good if member can be download this site, this website is okay and it can be designed ontology as well. Ontology and so hard to imagine the concept, knowledge, and put some related to between classes in detail in ontology. I introduced just a tool is good for now is repository. So our Protege, our language as well. It's good. It's good for.
I think this is a very, very good suggestion because this is exactly related to the other question about the visual tool, and this is the visual tool we should.
It is exactly what we need for as training material. You are perfect.
Yeah, this is very nice, Sarat.
Yes, because I ever use this tool to do research. Some part of my research is okay for the beginner of ontology. I just introduce for member if you interest in this tool, it's okay and can be apply your content in logic, in design ontology, knowledge engineering, and also proof in predicate logic as well because it's some kind like use some language in predicate logic and they can run our language and RDF as well. Okay, so that's my opinion.
I think it's a very good idea, and I actually suggest that if you can put this for the next meeting, if you have I don't know if there is a manual or something that something can be put online.
Very good, Dr. Varava.
It's a very good idea.
Yes, very good.
Okay, because I think many members so have problem in the beginning of teach some new courses we have decided. I concerned about it. Okay. Thank you.
Thank you. No, thank you. Thank you. You. That's okay. Then.
Because I have heard Amanka, Amanka asked the tools and members.
Yeah, exactly. Yes.
Okay. That's the same tool Prabhat also mentioned earlier. One of the tools that we could use.
Exactly.
If we want to talk about a tool, I think every member of a task of a working group should contribute because the coverage is so wide, so wide. So for example, your tool, I didn't know. So if you ask me to do that, I didn't know. But it's really helpful and relevant to put it in the training material.
Well, yeah. Yes. Well, Marcelo present the contents is perfect, but I just concern and introduce some highlight.
It's a perfect addition. That's
okay, that's good. Okay.
Some comment from our Indonesian colleague.
For my knowledge representation course, we use Protege tool.
Oh.
Okay, so that's interesting also. So
could you switch on your video?
Sorry? My connection is really bad, so I'm sorry for that. Maybe next time. Okay, and I think this class is a heavy one, right? So yeah, the challenge is to how to get the people, student and engage. So in my class, sometimes I skip the theoretical part and more to the applications. Like for instance, and when talking about the ontology, I spend a lot of time is exploring the Protege because for them it's more interesting than talking about the theory. And also when semantic web, we explore several technology in that area. Like also, I didn't see about the knowledge graph. You covered the knowledge graph?
Yeah, conceptual graph. Yes. It's
the knowledge graph like DBpedia, LinkedIn, or
yes.
Google.
Yeah, they are treated in 1.2 and 1.3. Yes.
That kind of stuff very usually interesting for students because they want to see how Google do that, stuff like that.
Yes.
That's my opinion. Thank you.
Yeah, so yeah, indeed, you are right. I mean, the approach I've taken here is a bit theoretical, but I think that supplementing or substituting even with some more applicative way, so that like the tools using Protege, I knew the name, but I could not remember. But now that I saw, it's very nice. I never used it, and I think it's very nice. This would be perfect for the course. So yeah, so repeating again that the proposal that Dung was saying, yeah, I think that at this point, we can discuss next time, the next meeting we are doing in 1 month or two, that discussing the different proposals, how every partner sees their own course. And you can use this material, but you can use other material like the using Protege, for example. Personally, I will not completely delete all the theoretical part. It's important that the students knows a bit of how things works, what is behind the tools, not just using the tools. But using the tools is also important because it's make more engaging.
Yeah.
I would suggest that maybe we think about next time when we meet in our working group, everybody send in what we have done or what we plan to do, and when we can see the view, and then we try to integrate that. As a preliminary view, and then things will be worked out in the next online meeting. What Marcelo presented is like overall framework that we can fit, almost everyone can fit in, or some part of it. Dr. Cameron, some comments?
Because the content is very broad, and the formal guideline should be present.
Could you speak louder?
Because the content is very huge, it's broad. The formal guideline for selection, how to shape the course, we require the guideline. That is my comment.
Yeah, that is something which I cannot answer, because it depends also on the knowledge of the teacher, you know your students. So I cannot say how you have to select the material.
Yeah.
I can give suggestions, like I did, for example, the complexity, you can skip it. I can say, like also Dung was saying, maybe you can skip also the answer set, all the other part, and just concentrate only on the prologue part. But it's you, the one who has to decide, because at the very end, you, not personally, the teacher who was going to teach this course is the one who has to be there in front of the class. So I cannot decide for him or her, sorry, by the way.
Yeah. I saw a lot of mathematics.
Yes.
Yeah. I wonder how the student can be survived.
No, well, it depends. It depends. I don't know. That's maybe also a bit of my ignorance, I must say. In
Because
Europe,
nowadays it's not fun to teach a lot of mathematics in computer science. The computer science student nowadays, they don't like mathematics like the old school like us. That's
yeah, but here we go to more philosophical discussion. So that's I don't think that is a reason why we should do less mathematics in the courses in our mostly undergraduate courses, because the students, computer science is a discipline which is a science, and I want there to say that yeah, we're not only to apply things, so we want to find also new method, new technology, and this requires that we have to have some background in the mathematics. Maybe not everyone will like it, I know that, but still I think that even in courses like machine learning, it's very, very important that students knows about statistics. They don't have to not just learn to use Python. They don't have to learn using a library. Of course, they also do this. It's part also the skill, but it's not the only thing. They have to know how it works internally also. They have to understand how the algorithms works and why it works. And that's the mathematics behind it.
Yes.
And the same thing for statistics is for machine learning. I would say that for knowledge representation is logic. Yeah, there is a logic behind it, and that logic it is what it is. You cannot make it easier than what it is. You can make more funny to learn, but it's something which must be learned. So a basic on logic, I think this should be actually available to all computer science students, all of it. Yeah.
I agree, but the student may not agree.
Yeah, sure, I understand. So that's why we have to try also not to be over exaggerating. I agree with that, but I don't want to find compromise in the sense of eliminating everything and just giving only application, but just try to understand what is behind it. And again, like the example of the complexity, we don't need to go into the details how complexity is really calculated. That there are Turing machine, that there are all transformation, and that they have to be done formally by means of function and so forth and so forth. But all this we can put under the carpet, but it's important that they know that there are complexity classes or that there are problems which are unsolvable. Or problems which are solvable but are untreatable. So these things are one can say it without just going to the details. And logic, yeah, something can be said and make more fun, for example, by using the tools in parallel. So if you just use the ontology, you just say how it works, the theory, and maybe you have a very sad lesson, but then in parallel, you just show how to use it with Protege, for example, like Fararat was suggesting. To use that, and then immediately you see in picture, and you can see how it works. Then I think is that's the best combination. But don't give only one thing.
So
but that's my opinion. Okay? I know it depends also.
Stop here so that our colleague could add some rest for the next session.
Have a lunch.
Thank you very much for